in collecting and computing the equilibrium points of such nonlinear systems. Okay, so where the dynamics does not exist any longer, or the dynamics fades away. Okay, and things become constant in time, or zero. Why not? And I showed you a few interesting models, nonlinear models. We are going to see a few more along this lecture. And then we were discussing classes of nonlinearities, and we were talking about saturation, sector nonlinearities, as well as hysteresis, for instance, nonlinearities, and so on and so forth. So the idea is that at this point, it's handy for us, okay, to define and to work with the so-called weak nonlinearities, such as the pendulum or most of the models I showed you earlier, okay? Why? Because in this case, we can easily define the concept of solution, okay? And we can actually visualize and analyze such kind of solutions, okay? Whereas in the case of the very strong nonlinearities, depending on the type of nonlinearity, usually you must define a concept of solution every time, okay? So we are going to look at this kind of models, okay, like I showed, the neuron or this guy, which is the pendulum, which are going to carry on studying throughout this lecture, okay? This and all sorts of variants of this of such equations, okay? So this is the most general in some sense, and we can see the notion of pendulum in many ways, okay? So please do study this pendulum guy because it's the benchmark example of nonlinear systems, is if you like, the mother of all examples for nonlinear systems, okay? And all the concepts and all the ideas we are going to emphasize in this lecture, they can be they can be straightforwardly in some sense, or they have a very strong one-to-one connection with this pendulum example, okay? So finally, the end of the discussion last time was what's linear versus nonlinear. Okay, so if we are system engineers or electrical engineers, we remember from circuit theory or systems theory or control theory or other things related to such fields that we could use the superposition principle and we could get transfer functions from all sorts of linear differential equations, and we could do the frequency domain analysis and the Laplace computation to recover the time domain response of such systems, okay? This was all based, or this was all possible thanks to this very strong and restrictive, in some sense, assumption of linearity, which now is gone. Now we have no discussion about linearity any longer, in the sense that if we are to describe an input-output system, okay, a system, any system, okay, which receiving an input u and an output y, and this is the operator t, defining in some sense the system, and the general relation is this one. Linear meant that t of u, linear is t of let's do the most general version using also some constants. So t alpha 1 u1 plus alpha 2 u2, okay, is alpha t u1 alpha 1 t u1 plus alpha 2 t u2. So this is linearity. This is linearity, okay? And this is equivalent to the so-called super superposition principle. Yes, which is very strong. Okay, well, when this is gone, nonlinear, this is also gone. So we cannot have frequency domain any longer. We cannot just add the effects of different causes and then sum them up and get the effect of the multiple causes together. That's not possible any longer. Okay, and this changes the view of things totally. Okay, this is totally changing the view of things. So we have to return to the basics. So we have to work now with differential equations. X dot is fx. This is an ordinary differential equation. F is nonlinear. Okay, so we do not have the superposition principle any longer. We have to work and to study and to understand this equation. For the linear systems, however, we used to do that because we used to study Ax dot is Ax. So this is a particular case. This is a particular case of this equation, okay? This is the linear version, okay? This is the linear version. I remind you that f is defined on Rn and takes values in Rn, okay? Now this is, in the linear case, this is the shape of function f. And we have all the necessary tools, okay? So here is linear algebra. Linear algebra was a necessary and sufficient tool to describe the functioning or the functionalities and the properties of such systems. Yeah, we remember we used to have responses, okay, responses, evolutions, because we could easily solve this equation, and we remember that the evolution, yeah, xt or x free, the free evolution of this guy is the initial condition x naught, because all of these systems can have initial conditions, or are defined by initial conditions. Okay, x of 0 is x naught. So this is x naught exponential of at. Okay, and then of course it's also the forced evolution. The forced evolution, when you have here an input u, we used to do that as well, plus b u. Okay, and then you have the forced evolution, an integral, okay, from 0 to t, exponential t minus tau b u tau. Okay, so this is the forced evolution. Okay, and the total solution of this guy, so the full solution of this guy was xt, was x free of t plus x forced of t, which is all very nice. Again, if you look at this guy, it's superposition. It's some sort of superposition because it's a linear differential equation. You add two effects of two different causes. One cause is given by the initial condition. The other cause is given by the input u. Again, superposition. Well, it's all very nice, and you have the solution. You have the linear algebra. So from this guy, you can easily extract properties such as stability. Okay, stability, which is very simple because you need its exponential. So e to the power at goes to 0 if and only if the spectrum of the matrix A, okay, the spectrum of the matrix A is in C minus. Okay, well, spectrum of the matrix A is the eigenvalues of A. Eigenvalues of A. We are going to recap some of these notions. Okay, so this is stability. Then you have other properties. Okay, you have other properties: controllability, observability, so structural properties. If you have A, B, structural properties, and so on, because it's all very easy. And here, in this case, you have a single equilibrium, one equilibrium point, x equal 0, x star equal to 0. Unique. So it's all revolving, or all around this point, equilibrium point, well, x naught. Well, here things are different. What is the solution? The first question. And once you understand what the solution is, and all the math and the whole tools, all the tools behind it, and numerical integration, like you saw, and you'll have an exercise about it and so on, then you ask yourself about stability. And now stability question is stability of the system, or is it stability of an equilibrium point, so of the trajectory going to a constant? Questions we have to answer ourselves. Okay, and then what is evolution? This is all related to evolution and response. Okay, so we have to study thoroughly study all these notions before we can do anything. So before we discuss control, we have to be able to understand the way we analyze such systems. Okay, and to do that, we start from scratch, and we start with a very simple case, simple but non-trivial, mind you, simple, however non-trivial, the case of first-order systems. Okay, this is the discussion we start today. Okay, first-order systems. It's a simple, like I said, but non-trivial case. So we address, as you see, fundamental issues: the existence and the uniqueness of solution. Okay, so what about the solution? And the so-called Lyapunov. We introduce the concept governing stability for nonlinear systems. Okay, and in general for dynamical systems, the concept of Lyapunov stability. Note that the state space is the real axis. It's the real axis. Okay, is the real axis. So what is a first-order system? First-order system is a system of this type. X dot is f, x, and u. This is the dynamical part. Okay, this is the dynamical part, and the measurement part, the output. Okay, where x is the state of dimension n, u is the control, and y is the measured output. So f is a real function. F is defined on R times R from the input. So this is from the state X, and this is from the state from the input U, valued in R. Okay, it's just a function. It's just a function. Okay. An example is the so-called Josephson junction, which is this circuit with a nonlinear inductance. Okay, circuit with a nonlinear inductance, and let's do some analysis about this. Okay, so we first, from electrical circuit theory, we recovered the notion that the current through the inductance L, is a harmonic signal, is of amplitude I0. And so it's I0 sine k phi L, where phi L is the magnetic flux of the junction, and I0 and k are constant. And now, so this is the law that governs. This is the law that governs the current through the inductance L, given by the inductance L. Okay, so probably the state will be phi. The state will be phi. Okay. This is nonlinear, okay, and we also, okay, okay, magnetic flux, okay, and we have the Kirchhoff's laws. We have Kirchhoff's laws, okay. We have here Kirchhoff's laws, current laws, okay, this node, for instance, and we also have a loop, yeah, a current loop, and we do have Kirchhoff's laws, yeah. So I don't know. You can say here IC and here IR, okay, and you have the first law of Kirchhoff. Kirchhoff was born a few days ago, actually. 2 days ago should have been his birthday, by the way. Great physicist. Anyway, so IR is IL plus IC. Okay, so the current through the capacitance C and the current plus the current through the inductance L, or the inductor L. Okay, and now since we know the relation that current is the derivative of the flux, okay, this is something known from electrical engineering. Okay, we can recover equation number 2. So this is a first order differential equation, scalar differential equation, because x is, which is phi L, okay, belongs to the real set. Okay, and I0 is the input signal. The input signal which is given by this current source here. Okay, well, now the question is, what are we going to measure? So any model depends on the measured variable. Okay, so taking into account what you're going to measure, you get a specific model. If you change the measured variable, the model changes as well, right? So we have to be careful, and we have to be careful of about choosing the measured state. So the choice of the output depends on the problem. When measuring the current in the junction, we have the output, which is exactly the current IL. So we would like to measure the current through the inductance L. Then this is the output. However, if you like to measure the flux, if you can measure the flux, you can take this output. Okay, so the model changes. Okay, because changes the measured output. But these are also real values, okay? These are also real valued, okay? Fine. Right. Good. So this is for an example, a good example of a linear a nonlinear scalar model, okay, and of course we can numerically integrate this guy. Let's see if we can do that by ourselves in MATLAB. Okay, I'll share the MATLAB screen in a minute. No worries. Teaching linear control software. Let's see. Let's open this guy. Can you see my MATLAB screen? Huh?
Yes, of course.
Right. Open. No, not open, but let's change the name of this guy. Call him Josephson junction. So the equation is here. What? Minus r. We have to define all these variables. Minus r I0 times sine of k times x. Okay. Plus I don't know if this guy knows about Heaviside. Huh? Heaviside. I don't think he does. Let's put it like this, plus 1. The initial condition. Okay, this is the what? This is the time domain where the solution, we'd like to simulate the solution on, to integrate the solution. Let's take r equal to 1, k equal to, I don't know, pi over 3. It's not capital K, but small k, yeah? What else? I0, right? Let's take I0, I don't know, half. We don't like such a large amplitude. Okay. Plot. Okay, let's take this one again. I'll show you why this plot is very important in a minute. I'll tell you why. Control C. Okay, solutions fx grid. Let's see if it does something. Add to path and run. It's running. Well, it does something, huh? It does do something. You see? So this is this here. Plot tx, I should say y label the solution a x t and label time. Okay, let's run this again. Okay, so this is the solution. Okay, x, you see, probably it's unstable, and this is the plot of, let's make it also 50. The plot of fx versus x. This is the plot of fx versus x. Well, if you look at the first graph, you realize that this solution is not going to an equilibrium point, right? Can you see that? You can see that, right? So there is no equilibrium here. Look, there is no equilibrium here. It's constant. It's monotonously increasing. If it's monotonously increasing, there is no equilibrium possible, right? probably 0 should have been an equilibrium point, but it is probably unstable because if you can see the trajectory runs away from 0, is fleeing 0, right? So probably the system is unstable. Now the question is, if we look at the second graph, which is the dynamics F versus, here I didn't write, let me make this possible as well, X label. Okay. You see, look here. Let me run this again. Okay, so this is Fx versus X. You see? So this is the dynamics versus the solution space. X is the solution space, okay? Can you notice anything? Look at the bottom part of the graph. What does Fx not do? What does Fx not do? Hmm? Fx is never what?
I would say it's periodically, but I don't know.
Is what?
It's like periodically, it's like repeating.
Okay, it's periodic. Okay, that's fine. It's periodic. I agree. But there is another phenomenon. You see, it starts from 0.5 and goes upwards. Fx is never cutting. You see, is never cutting axis X. So Fx is never 0. You see? You see? Fx is never 0. True?
Yes, of course.
So if Fx is never 0, what does this mean? You never have what? If Fx is never 0.
Like there can't be in saturation because it's always
No, not
changing.
saturation. This is not about saturation. What does Fx equal to 0 mean? If you have the differential equation x dot if is Fx, what does Fx equal to 0 mean? We discussed that.
That there is an equilibrium point.
Okay, but here Fx is never 0, so
there can't be an equilibrium point.
Exactly, it will never go to an equilibrium point. So there is no, it's constantly dynamical. It's dynamical, always. It's in dynamics. It never goes to an equilibrium point. Okay, it never stops. In some sense, it never stops. Okay, at least with the data we have here. At least with the data we have here. Okay, it never stops. Okay, so I would say this is quite interesting because we are going to see all these properties actually properly formalized. So let's kill this screen and go back to the other screen. Okay. Okay. Right. So now let's look at some theoretical stuff before we do anything. Okay. Let's look at some theoretical stuff. So this is well, we assume now that we have no control input. Okay, so we'd like to study the free evolution of such a system. So this is a nonlinear scalar system. This is the dynamics. X dot is Fx, and this is the measured output. Okay, and how do we solve such an equation? This is the question. Can we solve this? Well, fortunately, in this very simple case, we can. We do use the separation of variables. We separate the variables x and t, time, and we get such a relation. Okay, we now integrate on each side. On the left side, we integrate by x, and on the right side, we integrate by t. We can do that. Mathematics allows us to do that. Okay, so the integral in 5, this integral is a scalar integral. So, and is a scalar, it's a scalar finite integral. Hence, we always get a solution. We just need to be very good at math. If we're good at mathematics, we can easily compute this integral. And I showed you last time a little bit about this. Okay. So the integral in 5 says here can be determined by elementary manipulations. Hence, you can always write this. So integrating the left side, you get some function depending on x of t and on x0, the initial condition, of course. And on the right-hand side, you get the time t. Okay. So in this case, you can easily compute. Say for instance, if phi is invertible, you can easily get xt to be phi inverse of t and x0. Okay, phi inverse of t and x0. You can do that. Okay, because we just said that our functions are continuous. Okay, there are no problems. Okay, so in this case, we can get an explicit solution of the Cauchy problem. An explicit solution of the Cauchy problem. Cauchy problem is the problem to solve a differential equation, defined by the initial condition, okay, and the time. And in general, we denote it by in this form: x of time and the initial condition x naught. So this is sort of easy at this level. Okay, this is kind of easy. Example. We have examples here. Okay, so we have x dot is minus x squared. Okay, so you just separate the variables, so you get integral from x0 to x of dx over x squared equals time. Okay, and the integral of x squared is actually x to the power minus 1. So it's 1 over x between x0 and x. Okay, xt. Okay, you can write it like this. And this is time t. So this is equivalent to 1 over xt minus 1 over x0 equals time t, and so on. Okay, you can do the computation. And here, if you remember last time, we could emphasize very easily the finite escape time given by the value of the initial condition. Okay, so if you take the limit here, okay, limit when t goes to 1 over x naught, okay, t larger or t smaller, whatever, of xt, this is infinity, plus minus infinity, okay? So this is a vertical asymptote, hence this is finite escape time. Finite escape time, right? Okay. The second example, which we are going whose computations we are going to find later, is the example of x dot is x squared minus x. This is related to the Riccati differential equation. Well, anyway, here you get integral from x0 to x naught to x 1 over x times x minus 1 dx equals time. And you solve this integral how? Elementary factors, okay? You split this into simple fractions, into simple elements. Yeah, okay. So this is what? This is integral from x0 to x1 over what? X minus 1 over x. True? Correct, huh? This is correct. Because this is x. If you do the calculations, okay, this is x minus 1 minus 1 is plus. Okay, it's correct. Yeah. Dx equals t. So this is ln natural logarithm x minus 1 x0 x minus natural logarithm x x0 x equals t. And now we use a logarithm property, so we have ln x minus 1 over x between x0 and x equals t. Okay, and then since this is invertible, just like I said earlier, you can easily apply the exponential. You can easily apply, okay, you write this properly. So this is ln x minus 1 over x minus ln x naught minus 1 over x naught is t. So ln x minus 1 over x is t plus natural logarithm x naught minus 1 x naught. Okay, and this is a constant. You can call this alpha for the sake of simplicity. Okay, and then you get that the exponential, x minus 1 over x, okay, is t exponential, sorry. It's an exponential times, and the exponential, because we use now the property of exponentials, okay, this is times x naught minus 1 over x naught. Okay, and here you can easily do the computation and determine x. Okay, it's not difficult. Well, so first of all, you try to compute the solution. Fine. But then it's interesting to see the equilibrium points. The equilibrium points. Okay. In this case, if you have the explicit solution, you can take the limit when t goes to infinity. Okay. Right. However, the equilibria are computed solving equation fx is 0. This is how to determine the equilibrium point. Okay. Now, if x star is an equilibrium point, so if x star is a solution of the equation fx equals 0, then xt and x0 equal x star for all t. This describes a full trajectory, a constant full trajectory. So the equilibrium, when you have the solution space, so this is x, this is time. This is how equilibrium points look like. These are equilibrium points, okay? This is x star 1, x star 2, and so if you have n equilibrium points, assuming, okay? So these are equilibrium points, okay? These are equilibrium points, constant trajectories parallel to the horizontal axis. This is what the equilibria describe. Notice that, okay, this equation is a single unknown equation, so this is easy to solve in general. Very easy to solve. However, when this problem, the dimension, so when x is a multiple, is a vector, okay, this equation becomes a system of nonlinear algebraic equations. Sometimes this is easy to solve. Most of the times this is difficult to solve. And sometimes the problem of determining the equilibrium points can be really cumbersome and tedious and requires special algorithms such as Monte Carlo search, for instance. Okay, so these are the search of equilibrium point sounds like an easy problem. Well, let me tell you that it's not. Okay, it says here, in general, determining the equilibrium point is a difficult task, taking into account that one has to solve a nonlinear system of n equation and n unknowns for nth order system. So this can be, like I said, a very difficult task. Okay. Well, now we need to present some ingredients. Okay, we need to present some ingredients of nonlinear systems, so we can just mind our business afterwards. Okay, we can mind our business afterwards. Right. That is, we talk about the existence and the uniqueness of solutions. This is very, very important. Okay, this is very important. Consider the differential equation x naught is fx. Okay, and this is given by some result from mathematics, which of course we are not going to prove, or probably we don't even know how to prove this. And okay, and we don't even know how to prove this, but we just take the result as it is. Okay, makes sense. We are here to study the systemic properties and not necessarily to be able to prove deep mathematical results such as this one. So having the differential equation x naught is x dot is fx, defined by 8, where f is satisfying a so-called Lipschitz condition. So there exists an L such that the distance between any points is upper bounded by this constant times the distance between the points where this function is evaluated. Okay, in some sort of neighborhood of x of radius r. Okay, then there exists delta positive such that equation 8 has a unique solution on this neighborhood. Yeah, if the distance between two moments in time, between the initial moment and the moment t is less than delta. So this is local. That's what it says. So it says here that if your system, your function f is, say, continuous or smooth, which is the best case, or whatever, piecewise continuous, say, then locally you can define a unique, you can define a solution, a unique solution actually. But this is on a very small neighborhood. So this is a local definition. Okay, so the solution has a local existence, it says here. So extending the solution for any moment time, okay, outside this interval of length data, usually is not possible. Is not possible. Okay. In the case of linear systems, this is always possible due to linearity, because they are global. So all the results we discuss for linear systems, if you remember, they're all properties of the system. So they have this global global attribute, if you like, okay, this global property. Whereas in the case of nonlinear system, this is no longer possible. We cannot define at this point. There are results of global properties, of global stability, or global solutions, but these are very, very difficult and usually very hard to prove, and usually very conservative in the sense that they are specific to limited classes of systems. They are not general, they are not valid for all nonlinear systems. Hence, is much better and it's wiser to discuss local solution of such systems. This is also not possible because of nonlinear phenomena such as finite escape. So how can you extend the solution on an infinite time interval when you know that the solution might exhibit vertical asymptotes, these weird discontinuities? So this is not possible. So once again, we talk about local solutions. Okay. Now, for instance, we go back to the example of this differential equation. Okay, and we stopped at when doing the computation. We stopped at this point. So essentially, here we further get that. Oh, sorry. Here we can further write that 1 minus 1 over x is x naught minus 1 over x naught exponential of time. So 1 over x is 1 minus this constant exponential of time. Hence, x is 1 over 1 minus, or we can say here x naught. Let's just do the full computation. Let's say here x naught. And here again x naught. X naught minus 1. Okay? So this is a way to generally write such a solution. Okay? So we have all the computations done for this equation. We have all the computations done for this equation. All right? So now if we go back to the slides, okay, we see here that actually this is the solution we discovered ourselves, performing the simple separation of variables principle. Okay, we get the solution, the expected solution. Okay, now of course that the solution we don't stop here. The solution depends, or the shape of the solution, the trajectory of the solution depends on the initial condition. The initial condition is crucial when analyzing nonlinear systems. If the initial condition is negative, we can rewrite 11 in this form, okay, where we replace x naught with minus absolute value of x naught, because x naught is negative. Hence, if you look at this guy, this is negative. This is negative. And it says here, furthermore, this function is increasing for any positive time, because when the time grows, this guy is growing. Okay, so this is decreasing. Increasing, and furthermore, because of the negative here. Okay, and furthermore, when t goes to infinity, this guy is going to 0. This guy goes to infinity. Okay, when t goes to infinity, this guy goes to infinity. Hence, the whole solution is going to 0. There is no finite escape time here. You see, there is no finite escape time here. Okay, so this solution can be extended between 0 and infinity. So you can just continue the line. You can continue the line from 0 to infinity. And taking a closer look, finally, this solution will go to 0. But who is 0? What, or even better said, what is 0 for the system? We see that F0 is 0, hence 0 is an equilibrium point of this guy. 0 is an equilibrium point of this guy, because first of all, when you start nonlinear analysis, you compute equilibrium points. Equilibrium points. Solve fx equal to 0, which comes from x dot equal to 0. Fx equal to 0, this is equivalent to x squared minus x equal to 0. This is equivalent to x times x minus 1 equals 0. So we have two equilibrium points. X star 1 is 0 and x star 2 is 1. We have two equilibrium points, okay? We have two equilibrium points. And look at this solution. So if the initial condition is negative, let's try to do some plot. So this is the solution x, this is the time t, and if I start from negative, okay, this here is x0 negative, then the theory is telling you that this is increasing up to 0. This is increasing up to 0. This is what it says here, okay? This is what it says here. It's monotonously increasing, okay? And finally going to 0, because this exponential is going to infinity. Very interesting. Right. Okay. It says here that for t negative, one can find this guy. So on the positive natural, okay, increase of time, there is no finite escape. However, in the past, okay, if you look at this guy, there is some constant a where this is 0. So essentially, if you solve the equation, solving minus x naught plus 1 plus x naught e to the power t equal to 0, and we have to extract t, okay? So this is equivalent to e to the power t is x naught over 1 plus absolute value of x naught over 1 plus absolute value of x naught. Then you get t is natural logarithm of this guy. Wow. So there exists t such that x not x0 but x is going to plus or minus infinity. You see? So it says that there exists a value of time, negative time, okay? This is negative time. And this actually comes like this. So in negative time, this is coming from minus infinity. So there is a vertical asymptote. It's finite escape time. It's finite escape time. And it shows you explicitly in this formula. We've just obtained a vertical asymptote for t equal to the constant a having a depending, yeah, this is depending on the absolute value of x naught. Okay, so in negative time, we cannot extend the solution beyond this point. We cannot extend the solution beyond this point in time. Okay, this solution does not exist on the left side of the value a. Interesting, huh? Another solution is what happens if x naught is less than 1. Okay, what happens if x naught is less than 1? Then, if x naught is less than 1, between 0 and 1, okay, this is always positive. Okay, so x naught plus 1 minus x naught exponential of t is positive for all t. Is positive for all t. Okay, and all right, and this is positive, so for x naught between 0 and 1, x is positive for all time. X is positive. Right. X is positive for all time. And then when t goes to minus infinity, this guy goes to 1, it says here. This guy goes to 1 because this is 0 and this, this is 0, yeah? So if t goes to minus infinity, okay, e to the power t goes to 0 when t goes to minus infinity. We know that. Hence, the whole solution x is going to 1. And if when t goes to infinity, of course, this limit, the solution goes to 0. So the solution is bounded and can be extended on the whole real axis, it says here. So if x is between x naught, call this 1. So if x naught is here, okay, the solution is something like this. And you can extend it on the whole real axis, okay? This is your solution, okay? What happens now if, and the final situation is what happens if x naught is greater than 1, okay? If x naught is greater than 1, again, you can easily compute a moment in time to find a vertical asymptote. You can do the same computations as in situation A. So you repeat the procedure of A. So there is a constant C positive such that the denominator is 0 for t equal to C. Hence, we get again a vertical asymptote. So when x is here, essentially, this is C. It's something like this. Okay? And probably when t goes to minus infinity, it goes to 0 in negative time. Okay? So if you look here, this is the copy of this guy, yeah, in some sort of mirror with respect to this oblique axis. Okay? So it's very interesting. So we realized that the different equilibrium points and the different initial condition determine bands of solutions. Okay? So if x naught is less than 1, then x is less than 1, you see? If the initial condition is less than 1, the whole solution is less than 1. Hence, we call the set 0 to 1 an invariant set of the system 10. Similarly, minus infinity 0 and 1 infinity, they say, those two solutions that copy each other, are invariant sets of the same equation 10. Okay, we have two equilibrium points. I showed you that. X is 0 and x is 1. The trajectory getting close to 0 and away from 1. We can see that. So they are all going to 0. Where is it? So you see? And so it's going away from 1 and going to 0. Away from 1, and going to 0. Hence, can we say something? Can we assess the stability of these two trajectories, 0 and 1? Can we say something about the stability of these simple solutions, 0 and 1? Okay, so this is x double star, and this is x star. What can we say? Can we assess the stability of these two guys? Which one do you think is stable and which one is not stable, please? Can you answer this question for me?
I would say that X star.
Which one?
The lower one, X star, just start.
Okay, x star equal to 0, so and this is 1. Yeah. So which one is stable and which one is not? If you can say again.
X star equals 0, but it's just a guess.
Is it stable or not?
I think it should be stable.
You think it should be stable, and the other one probably unstable. Just like the pendulum, if you remember. Okay. Indeed, this is true. We can, because all the trajectories are going to 0, we call this guy an attractor. And we call this guy a repulsor. Because it pushes away all the trajectories. Indeed, x star equal to 0 is an attractor, and x double star equal to 1 is a repulsor. Which is stable? Of course, the attractor is stable. The attractor is stable because all the trajectories are drawn to this guy. Okay, so we can understand a bit of notion of stability in the sense of, depending on where we initialize the system, or depending on how we perturb at t0 the constant solution, depending on that, and depending on where the trajectory goes, we can assess the stability of the trivial trajectory given by the solution of the equation fx equal to 0. And here we do have the MATLAB simulation. Let's try again. Let's look again at MATLAB. Why not? MATLAB is good. I think it's actually this. No, this is the Riccati one. Let's go to this one. Okay. Let's run this. You see? So here I have an initial condition which is negative. Look at figure 1. Okay, let's repeat this X label, Y label stuff, because this is important. Copy, paste. And here, okay, excellent. Oh no, here I have already have X. Let's run this guy again. Yeah. Okay. So you see, yeah, the initial condition is negative, goes to 0. The initial condition is positive but less than 1. Look, it's going to 0. Yeah? It's going to 0. So the bands, here we see the bands of solutions, and this is larger than 1. say 2. Look, vertical asymptote in 0.7. 0.7, you have a vertical asymptote. Yeah? So we do emphasize what we found earlier. And this is the graph. This is the graph of fx versus the solution x. What can you see? The graph has here. I should make a zoom. Oh, sorry. You see, we have here two equilibrium points, 0 and 1. Okay, 0 and 1. Yeah. Let's make this 50 because I think it's a better. We take more points, okay, or even a 100 because then the graph is much better. Yeah. Otherwise, we do not properly see. You see? Oh, we are supposed to have, look, two equilibrium points. One is in 0, the other one is in 1. Okay? In this area. Okay? And you can see, look, this is negative when going to 0 and then positive. Okay? Negative and positive, and then it's positive and negative. We'll see that these type of signs can help us determine the stability of the solution. So what we saw on the left graph, we can easily check on the right-hand graph of the dynamics, okay? On the right-hand graph of the dynamics. Now, actually, I was trying to show you and introduce to you the symbolic computation of Maple. I'm not sure if any of you has ever seen or has ever encountered Maple before. Maple is a symbolic tool, symbolic calculation tool. Mathematica is the other one. Apparently, Mathematica is much more evolved and has improved algorithms than Maple. However, Maple is covering a multitude of situations. Okay, a multitude of situations. Maple is made of packages, and in Maple you work with sheets just like in Excel. So these are called Maple sheets, not programs like in MATLAB, but Maple sheets. Okay, this is the interface. This is how it looks. Right. Now I'll try to introduce this to you. Let's see if I can do that. I'm opening any sheet and I'm cleaning it. Okay. So essentially, no, wait, let me try. Bear with me a minute, please have some patience. I'll try to find some peculiar simulations because I'm sure I have them. Just have a little bit of patience, please. I'm just asking you to be a little bit patient. Oh, but I do have here, okay? It's already made. So this is what a Maple sheet looks like. First of all, you need to properly load packages of tools, linear algebra tools, other tools of linear algebra, vector calculus. It's a specific and very important tool. You have polynomial tools, algebraic stuff, student linear algebra has some specific function, student calculus, integral transformations, dynamical systems, numerical approximations, differential equation tools, and plots. Okay? So this is how you define your differential equation. You just write this function, and then your You write this function, and then your differential equation is defined like this. So you see x dot is this differential operator, capital D. This is a prescribed, how do you call that? A prescribed function in Maple. You cannot just use D as a variable. You cannot use capital D as a variable. Not prescribed function. How do you call this? Dedicated variable. It has a specific name. It's fixed anyway. And this is the differential equation, if you can see it here. Okay, so when you do 2 points and equal means you attribute the value. When you do equal is just checking equality, like here. You see the difference. Semicolon equal, and then you have simply equal. So this is how you define your differential equation. Okay, and to solve it, you use differential solve of the system and the initial condition. ICS defines the initial conditions. ICS defines the initial conditions, which are written here. Okay, and you assume x0 negative. You can have this thing. So this is just like solving using the pen and the paper. Solving the pen and the paper. Okay. The first here, solve. This is the typical command to solve algebraic equations and algebraic systems. And this is used to find the equilibrium point. This is how to write a comment. So if you put this sign, before any piece of text, it's a comment, just like when you use in MATLAB the percentage sign. Okay. Okay, and look, it does solve the equation. It does solve the equation, okay? And then you try to solve giving a specific value because you want to plot this guy. You want to plot this guy, and this is how to solve. This is how to solve the vertical asymptote issue, and you call it alpha. Okay. All right, and so we check everything we have discussed so far using these lines in Maple. Then you numerically solve. In order to plot the solution using the function dsolve and asking or forcing it to use the numerical algorithms in a specific range. So here, if you can see, we can solve, and we can also do this in MATLAB with the linspace in both negative and positive time. And finally, you plot the solution. Okay? And then you do the plot of f versus x. Okay? So you can play with this guy. I can give you a MATLAB kit if you like. And I'm going to put all these files on in your Teams class of this lecture. Okay? So this is our look, the solution. You see, vertical asymptote. Is this okay? Guess so. ICS1. ICS1 is, yeah, when the initial condition is larger than 1. Vertical asymptote. Okay? Vertical asymptote, which is somewhere in a little bit on to the right of the vertical axis. The vertical axis. Okay? So you can also take 2 here and try again. Yeah, you see, to the right of the vertical axis, there is a vertical asymptote. Okay, now, if the initial condition is negative, I just put a minus sign here. You see, look, the vertical asymptote to the left of the vertical axis, and the equilibrium is 0. Okay, and the vertical asymptote is occurring in natural logarithms or logarithm of 2/3, okay, which is given by this floating number, okay, float number, minus 0.4. So here in minus 0.4, if you zoom, okay, if you zoom, you can see the vertical asymptotes. Okay. Usually we take smaller numbers, 0.5, and see if this shows. Of course, you can manipulate these images. Yeah, you see the vertical asymptote. This is much better visible. Yeah, because alpha has a larger value. Alpha has a larger value. I think we can do this thing. If you go to Access Properties, yeah, horizontal from -2. From -2 to 5. Apply. Now you can see the vertical asymptote much better. Okay, so I'm emphasizing the vertical asymptote because I asked him to have a small range here. Okay, and the solution going to 0. So we emphasize the 0 stable equilibrium point. The 0 stable equilibrium point. Okay. Okay. All right. This is a nice environment I'm showing you. I hope you can easily look and understand how to. You see, you can write functions here. You can write a lot of things. So you can look through the documentation of Maple if you like to work with it, and check it out, because I'm going to upload some Maple sheets for you to see some nice plots and results. Okay. All right. Fine. Let's go back.
Teacher?
Yes.
Can you provide us a Maple kit?
Yes, I can.
Okay.
So I'm going to upload it on the Teams class.
Okay, great.
I'll do that for you. But I will kindly ask you not to spread it around, because it's okay.
Sure.
It's not a licensed version. Let's put it this way. Okay, and follow the instructions on how to install it. There are instructions over there. Okay, but I'm just asking you not to share it too much. Okay, agreed?
Yes.
It's just for your own personal use. Okay.
Mm-hmm.
When you are at home and you like to do some work. Okay. Okay. And I'm asking you because I'm sure you have rights. Once you all have downloaded it, delete from the Teams class. Okay. Agreed?
Okay.
Fine. So this is the MATLAB simulation, the numerical integration, and I also showed you the Maple version of these things. Maybe if you learn a little bit of Maple, it can be useful if you have some nonlinear interesting problems, not necessarily dynamic systems, any other things. You want to solve equations, you need to solve this and that. Sometimes Maple can be useful. It has all sorts of simplifications, so Maple is quite smart in this, and Mathematica, I understand, is much better in simplifying expressions for you. Okay. Well, sometimes Maple fails to do that very well. However, I've used it in my research quite a lot, because when I deal with nonlinear systems, it's hard to use MATLAB. Okay. I mean, you do numerical integration, but sometimes maybe it's not possible if there are too many equations and so on and so forth. Right. So here you find the code I just showed you earlier. Okay. The code. You can use this code. I'm going to upload it on the Teams class, and you can check it out and you can play with it as much as you like. Okay. Right. So now we saw that we can plot things. Okay, and we can have very nice plots of things, and we can choose to check the qualitative behavior in the extended phase plane of t versus x. Okay, t versus x. For the sake of simplicity, you assume that f is an analytical function on the real axis. Okay. Hence, we get two situations. If fx, just like I asked you earlier on the Josephson guy, even if fx is if fx is never 0, so is not 0 for any x in R, it follows that f has a constant sign on R. Makes sense. It's either negative or positive. Agreed? And so does the dynamics. So the dynamics is always positive, or so the derivative in time is always positive and or always negative. Okay? Hence, all the solution in time, okay, if x dot of t, so if
Teacher,
x,
teacher,
yes.
I'm sorry.
Oh,
Did you?
check the screen?
Yes, yes.
I'm sorry about that. Well, never mind. I was just talking. Okay, you can if you see the slides on Moodle, you can open them yourself. You don't need to follow my screen, but fine. Sorry about that. Okay. So again, I'll start again. Okay, so we are at this point where we study the qualitative behavior in the extended phase plane. Okay, so we look at x as a function of t. So this is a function of t. This is defined on R, valued in R. And if x prime of t, let me put it this way, is always negative, then xt is always monotonously decreasing. So it never cuts the horizontal axis. The same goes for positive. Increasing. True? We know that from basic calculus. Right. Hence, there is no equilibrium point. That's what I'm saying. Since it's strictly increasing or decreasing, no equilibrium. It's always in dynamics. It's always in dynamics. However, if this is not true and there is a change of sign, if f is changing signs, hence if x prime of t or dot x dot of t, x dot xt dot is changing signs, then probably fx is 0 in some points. Fx is 0 in some points, and these points are the equilibrium points of the system. These are the trivial solution, xt equal xi, which are lines parallel to the time axis. I told you that earlier. Separating in, if we have p equilibrium points, you separate in p plus 1 horizontal bands of solutions. Horizontal bands of solutions, okay? This is the earlier solution. So this is for x dot is x squared minus x. This is the plot. Okay? You remember. Well, it should have been something like this, actually. The other way around, okay? You remember the bands of solutions. You can try to do this plot. You can try to do this plot, or we can try to do this plot for this function. For this function. You remember, yeah? T, x, and we had, oh, this is in general, okay? So for this guy, we had two equilibrium points. One was here, okay? So this is x star equal to 0, and one was here. You remember, yeah? This is x double star equal to 1. And we had the bands like this. Okay? This was the first band with the initial condition x not negative. Then the initial condition between 0 and 1, you remember, yeah? Was like this. Sorry. You remember this, yeah? X naught between 0 and 1. And then, if x naught was larger than 1, the third band the third band, so the solution was coming from 0. The third band was like this, with a vertical asymptote. Okay. Is it clear? And this is x dot equal x squared minus x. Is this clear? Questions, please. Questions, please. If you have any questions, please. No questions? Is it kind of clear of what I'm doing here? I know this sounds very simple, but I assure you, it's actually much deeper than it looks. Okay. So I'm asking you again, have you got any questions, please?
I don't.
Right. Okay. Fine. Okay. Now we have to ask a few questions, a few interesting questions, so we are able to understand each other and to understand things correctly. The first question is, can two solutions cross each other? This is the question. Look at this plot. Can any two solutions cross each other? What do you think? Yes or no?
No.
Of course not, because they are separated by the horizontal trivial trajectories given by the equilibrium points. Of course not. Explain why. I just told you why. Hence, any solution is itself contained in one specific band. Okay, it's contained itself in one specific band. Okay, horizontal band. Okay, right. Since f keeps constant sign between two consecutive solutions, between two consecutive equilibrium points, I would say here instead of roots. Okay, equilibrium points. A solution included in the appropriate band will be either monotonically increasing or monotonically decreasing. I said monotonously, which is correct. Monotonically. Okay, apparently this is also correct. So it's decreasing or increasing. Look at this guy. This is, if x naught is larger than 1, this one is increasing, monotonously increasing. Okay. This is monotonously decreasing. And again, this is monotonously increasing. Okay. So it's not changing the sign. It cannot change sign because it's between equilibrium points. So it's between two places where where x dot t is 0. Okay. Right. So this is basic one variable calculus. It's no novelty in this. Good. If a solution belongs to the band between two consecutive equilibrium points xi and xi plus 1, it will asymptotically go towards one of them and asymptotically leave, okay, one of them. It will tend asymptotically towards a limit or the other of the band, okay? Right? You saw that. Look, this guy. It's always increasingly going to especially between 0 and 1, okay? So this is between 0 and minus infinity. This is between 1 and infinity. But on this band, on this segment, it's asymptotically coming from 1 and asymptotically going to 0. We can see that. So this is always happening for this type of systems. Okay, for this type of systems. However, if a solution belongs to an interval of type minus infinity, equilibrium point I, or equilibrium point J to infinity, then one of the limits will be infinite. So in this case, you typically get a finite escape time. That's what it says here. So if the solution belongs to such a band, there's always a finite escape time occurring. Always finite escape time, okay? Always finite escape, not escapable, escape time occurring. Okay, it's always happening. Okay. Note that such equation with f at least continuous do not have periodical solutions. Do not have periodical solutions. However, if f is discontinuous, this is not true. Okay, because it's a different concept of solution. Okay, so the solutions we study here and the concepts we study here are for the particular case or for the specific case of continuous f's, continuous vector fields f. Okay. Now let's define. So we looked at these equations at first order. Essentially, up to now we just sort of made a discussion, a transition between the first order differential equations, or nonlinear differential equations, and first order systems. Now let's just define the first order dynamical system. What is the first order dynamical system? Is it the equation? Is it the solutions of the equation? A solution of the equation, or the solutions of the equations? This is the main question, and we have to properly define and fix such notions. So if equation 8, what's equation 8? Let's go back. This is the equation. If x dot is fx, okay, has a unique solution on R, okay, then the set of solutions defines a dynamical system. So the set of solutions is defining the dynamical system. Phi of T2 plus T1 and x0 is phi of T2 and phi of T1 x0. So the set of solution is defining the dynamical system. So a dynamical system on a metric space X, your space needs to be a metric space, is a function pi with the following properties. In 0, at t equal to 0 and x, it's 0. So this is the initial condition. So it satisfies the initial condition. Pi is continuous with respect to both variables, time and solution. And this group property happens with respect to the first argument in time. Okay, all right. So this is based essentially on the uniqueness of the solution. This is what prompts us to write such a definition and to define such a concept of dynamical system. Okay, so the dynamical system are the solutions, and they are described essentially by the differential equation whose solutions form the first order dynamical systems. Well, now we have to understand the concept of trajectories in the state space, which here in the case of first order systems is the real axis R. Under the same assumption, that is F analytic on the whole real axis, a trajectory defined on a segment of time tau 1 and tau 2 can be an equilibrium point, like this, a segment between the initial condition x0 and x, okay, like this, okay, Here, look, this is a segment. This segment here. Okay. All right. Or half line, half lines. You see, in this case, these are the solutions. Yeah, this is a segment. So, sorry, this is a half line. The same goes here. This is a half line. Look, from here onwards, these are the solutions. So segments or half lines. Okay, or of course, it can be the whole real axis. Okay, the entire real axis. Entire real axis. You can also have that. So these are the only possible trajectories on on the state space R. Moreover, the type of trajectory does not depend on the initial condition x0. Okay, any segment on a trajectory is passed in a finite interval of time. That's also true. Okay, because it's a segment. Okay. Now, equilibrium points. You see, now we look at this plot, fx versus x. Fx versus x. Okay. This is very important because why? We can easily determine equilibrium points on such a plot. You see, if you do this plot fx, so fx is x dot, okay? X dot versus x, you get here the equilibrium points. The equilibrium points are those points where fx is cutting the state space, i.e. the horizontal axis r. And now you can also, based on the sign of the function around the equilibrium point or in the neighborhood of the equilibrium point, you can determine whether that point is stable or not. So it is an attractor if this is positive and this is negative. Then this is a repulsor because the negative means the trajectories are going away from the equilibrium point. Okay, so positive means attraction to equilibrium point, and negative means leaving or fleeing. I like to see fleeing the equilibrium point. It goes away from the equilibrium point. Okay. So now we can also easily, in this case, we can easily assess the stability of the equilibrium points. Okay. If fx is never zero, like we saw in the case of the Josephson guy of the circuit, then to any solution, one associates the same trajectory, which is the whole real axis. Okay, that's the whole real axis. Okay, half lines are the trajectories between the equilibrium point and plus minus infinity. We saw that. And segments are the trajectories between two equilibrium points. Okay. The conclusion is that the equilibrium points are the essential guys determining the system behavior. Okay. So you look, if you remember from physics, you used to do static models. That was for a real cause, for a good cause, because the static model was telling you something about the dynamics of the system. Okay. And of course, we do have some examples we can solve. Okay. And we can look at their solutions. And I actually invite you to try to solve these examples yourselves. Okay, I do have, if I remember correctly, I do have materials with the solutions of such things. Maybe we can try to do these things in Maple. Why not in Symbolic? And you can do them using the pen and the paper. If we look on Moodle, let's go back to Moodle and see if I have already uploaded such materials. Okay. Now, where do I see Moodle? This is Moodle. Login. Complex, whatever, non-linear control systems. I see that this year they wrote them in English. Last year they wrote them in Romanian. Okay, so these are the papers. Oh, and these are look, these PDFs with solved. Yeah, the problem is that they're in Romanian, written, handwritten by myself. That's an issue. So here I was writing some examples of computations of some specific examples. Yeah, I have here the growth of the population in a fish pond, which is very interesting. Okay, and other examples. So maybe what you can do, and this is the Riccati equation we just saw earlier, solved here. Okay, so what you can actually do, you can Theodor and Andrei, you can explain these things to Florian in English based on these notes. Can you do that?
Well, yeah.
Okay, because here they are very. I'm trying to explain some of these things to him. Okay. This population in a fish pond is very interesting. Okay, let's have a break for a while, and then we'll think. I'm thinking of how to explain these things, or to try to do the examples here for you. Okay, let's have a break. I don't know how long it's gonna take, but I'll see you. I'll see you soon. Okay, just stay tuned. Right?
All right.
I'm back. Hello. I'm back. Anyone still around?
I'm back too.
Oh, lovely.
Yeah, I'm here also.
Okay, thanks. I'm sure you are. Because I honestly think you're the only ones left from this program. The rest left. That's what I heard. That everybody else has left. Right. I was telling you about these exercises. I'm going to explain them in English so our friend can understand. The first example is this guy. X dot is 2 square root x, where you do exactly what I said earlier.
Forgot to share the screen.
Oh, again, sorry. Sorry about that. Yeah, sure. No worries. But you know that you can look in the OneNote book of the lecture without me sharing the screen. You can just look wherever you like and follow my pen.
That's
you
true.
can do that. But anyway, let's just right. Now, can you see my screen?
Yes, it is visible.
Okay, thanks. Let me just check. Right. So I was saying this example, x dot is 2 square root x. Okay. First of all, we can, I just forgot to mention, so here is just a mention of the time of variable, separation of variables. Okay. Separation of variables. Okay. And this is possible, I was saying here, because this is a time invariant system. That's why we can do that, because the coefficients are constants, okay, are constant numbers and not functions themselves. That's why we can do separation of variables, okay, and reach this value here. Right. So I was saying we do separation of variables. This is very easy. We do integrate. You remember that integral of 1 over x dx, the primitive is square root of x itself times half. Okay. Right. So you can do all the computations and look, of course, because the square root is monotonically increasing depending on the initial condition. You have no equilibrium point. Okay. Look at this plot here. You have no equilibrium point, right? But the second example, I would say, is more interesting. This is funny because this is the growth of fish population growth in a fish pond or in a pond. Okay, you know what pond is, lake, a small lake. Okay, and usually ponds, just like lakes, can be natural or artificial. Well, never mind. And this is the equation, the scalar equation governing this. Can you see a similarity between this and the Riccati equation we discussed earlier? Can you see that? The Riccati equation earlier, was x squared minus x is x dot. Now this is, whereas the fish is x dot is minus x plus x squared. You see? So there is a change of sign. Okay. So this is totally changing what's going on here. We have here some coefficients, R and nu, sorry. No, R and eta. Okay. Eta is the lake capacity, is the pond capacity. Okay. Capacity of the pond. Whereas R, so actually this is the capacity is the growth rate when the rate of increase of population growth is 0. Okay, so this is the number of fish when growth rate are equals 0. Okay, and first of all we compute the equilibrium points. What do you know? The equilibrium points are similar to the Riccati equation. X star equal to 0, no fish, so empty pond. And the second equilibrium is X star equal to eta, full capacity. Yeah, the lake is full. Okay, and again separation of variables, and here you have all the explicit computation. Of course, the left term is you use simple fractions to solve it. Okay, and here is how to solve the simple fractions using residues. Using residues. Okay, this is some math stuff. Okay, and then when you do the computation, okay, you see here the entire computation very explicitly. Finally, you reach this solution, just like you saw earlier. Okay, you reach such terms. This is very much like the Riccati equation, but however, it's all different. We have a remark here, an observation, that for t equal to 0, we have the initial condition x naught fish in the lake, in the pond. Okay, initially. Okay, x naught at t0. Okay, then you see that usually you can have x0 larger than the full capacity or smaller than the full capacity. I mean, I would say larger or equal than the full capacity. Finally, the solution, when it is computed, it looks like this. So the final solution of this equation looks like this, or like this. Okay, and look, when you take t going to infinity, you go for t going to infinity. Okay, when t goes to infinity, no matter where you start with the initial condition, either here or here, you see that the fish population tends to fill up the whole pond. Eta is the full capacity of the pond. You see? So even if you have more fish, even if you have less fish, the stable equilibrium of this fish pond, okay, is eta. So eta, this is the stable equilibrium point. This guy is the stable equilibrium point. So the full capacity of the lake, so if you put 2 fish in the lake, finally, taking a specific, sorry about that, taking a specific growth rate, okay, even if you have 2 fish in the lake, okay, I would say 2 pieces of fish in the lake, because you cannot say fishes in English. Fish is plural defective. Okay, so fish does not support a plural version in English. So if you only put 2 pieces of fish, finally they will grow and grow until when? Until the whole pond is full. Nonlinear thinking, very interesting, huh? Same, if you put too much fish over the capacity of the lake, probably they won't have enough food, and taking a specific growth rate, some fish will die, but the fish will stay at the full capacity. This is the stable equilibrium point. Okay, the fish will never be empty to zero. Okay, so we will never go to the zero equilibrium point. It will never happen. So zero is unstable because no matter how small you make a perturbation, if you drop 1 or 2 fish in the lake, finally you'll get, with the food and everything and the growth rate, you'll get the full capacity. So zero is an unstable equilibrium point because the trajectory or the solution of this growth will always go away from zero, but the full capacity of the lake is the stable equilibrium point because no matter how much fish you fill up or you introduce in the lake, it will always go to the full capacity of the pond, even if it's too much fish or too few fish. Okay. Then we have the Riccati equation. The Riccati equation, which is this one, which we discussed. The Riccati equation is the opposite of the fish pond stuff. And here you have the full computation for the Riccati equation. Okay, the Riccati equation. So I would say this is minus fish, so to speak. And you have the full computations, negative, positive, all the graphs and everything. So you can study this and you can show this. We discussed earlier you can also show our friend Florian in English all of this stuff. Okay, and then we have some simple examples. Those are the examples you found in the lecture slides. We have the linear case with a classic solution we already know. So the linear case x dot is ax with a non-negative a. With a non-zero a. Okay, with a non-zero a, and you have the solution of this equation is x naught, the initial condition, times exponential of at. If a is negative, then if a is negative, look at the and this is very interesting. Look at the plot f of x versus x. F of x here is ax. This is fx. And because since a is negative, the slope is negative. We know that from simple geometry. When the slope is negative, you see the zero is an attractor. When the slope is negative, 0 is an attractor, so 0 is stable. When the slope is positive, 0 is a repulsor, then 0 is unstable. So this is another explanation of the fact that for linear systems you need to have negative and positive real parts of the eigenvalues of the matrix A. Okay? Okay. Where was we? Right. Okay, fine. Yeah. Well, then you have fx is minus x cubed plus x. And here you determine the equilibrium points. So right now you have with this function, you have 3 equilibrium points. You have 3 equilibrium points. We do an 11th grade plot of the function because that's what we're interested in. We don't look at the solution. Now we don't do, if you like, you can do yourselves the separation of variables. Okay. And find an explicit solution of this differential equation. Okay. Well, here you remember this plot from simple calculus, where you plot the sign of the function and you determine the monotonicity of the function. Okay, on specific areas, in specific areas. So you do that. You know that the derivative of this function is minus 3x squared plus 1. And the derivative is 0 in 2 points, plus minus square root 3 over 3. Okay. So 1 over square root 3, sorry. Okay, and then you remember this from simple calculus about the derivative. What happens to the so it's decreasing between minus infinity and minus 1. It's again, and then it minus 1 is 0. Then it's again decreasing between minus 1 and minus 1 over square root 3. Then it's increasing to 0, cutting the horizontal axis, then increasing up to square root of 3 over 3, then decreasing to 0, and then again decreasing to minus infinity. And then this is the graph. This is the graph. So you have 3 equilibrium points. The first one, minus 1, is an attractor. 0 is a repulsor, and 1 is an attractor. So what can we see from this plot? That if you have multiple isolated equilibrium points, their quality of being an attractor and a repulsor is consecutive one to another. So if the first one is an attractor, the next one is a repulsor, then the next one is an attractor, then the next. You can never have 2 attractors in a row or 2 repulsors in a row. You realize that, right? You cannot have that. You agree?
Yes.
So these qualities are alternating every time. Attractor, repulsor, attractor, repulsor, attractor, repulsor, and so on and so forth. And here is the solution. I solved this equation finally, and I found this solution. This is the time solution of this. And you see what happens, that indeed, when you take t going to infinity, you go to either the equilibrium 1 or to the equilibrium minus 1. Then you have x dot is minus x squared. A simple calculation. You have a single equilibrium point in 0, and this is a third situation we haven't discussed. It's a saddle point. This is a saddle point. Okay. Why? Because both signs are the same in this case. So this is a saddle point. This is called a saddle point. A saddle point, just like the saddle of the horse. It's a saddle point, okay? Look, by the way, this guy has a vertical asymptote in t equal to minus a, okay? This is a finite escape time example. And then you have x squared minus x, again, attractor, repulsor, and so on. Also, the same goes for the saddle point. If you have a saddle point, then the previous one is either a repulsor, and the next one is either an attractor. So the saddle point is always can always be between an attractor repulsor sequence. Okay, you can never have 2 saddle points consecutively. Again, for 2 consecutive isolated equilibrium points. Okay, the Riccati equation and so on and so forth. Okay. The question was that, is this a stable equilibrium point? X dot is minus x squared. Okay, here I was making a Lyapunov analysis. What's Lyapunov? Lyapunov actually is searching for an energy function of the system, if it exists. For physical systems, we know for sure there is an energy function, and actually any nonlinear system has an energy function. Unfortunately, we are not able to compute it most of the times, but it always exists, especially for the physical systems. Physical systems, they all benefit from explicit energy functions based on the variables, such as displacement, velocity, whatever. Okay. So what happens? What is Lyapunov saying? Lyapunov is saying a very apparently simple fact, but the proof is quite difficult. It says that if a system's energy, internal energy, is decreasing and going to a constant level or 0, then you have stability of that trajectory where the energy is constant or 0. Note that this is a sufficient condition and not at all necessary. You might have stable points that do not satisfy this property. Okay? However, if this property is satisfied, you're sure that that specific equilibrium point where the energy of the system is constant or 0 it is a stable, an asymptotic, actually even an asymptotically stable point. We're going to explicitly see these results when we talk about second order, second order and nth order systems, where we are going to see the general results of such. And this Lyapunov idea of energy also is yielding, and you can look in the book of Khalil, specific control, nonlinear control algorithms. They are peculiar to nonlinear control, so they are not possible. They are not given by linear stuff, so they are given by the nonlinear control, such as passivity-based control. Passivity is an energy property. We know that. Okay. Fine. So what happens? So you have an energy function, for instance, for such a system, you take this energy function. Usually energies are positive, okay? So energies are specifically positive functions, otherwise they are not energies, okay? So please let me just ask you, let me give you a cultural nudge and tell you that when you hear people saying about negative energy, they are essentially idiots. There is no such thing as a negative energy, okay? So you never, quote, radiate negative energy or emanate, or you never exhibit negative energy. This is plainly stupid because energy is a positive thing. Energy is a norm, by the way, mathematically, is a measure, is a two norm. So you can, a norm is positive by definition, by default. The distance between 2 points, it can never be negative. Okay? Energy is in the same class of measurements like the distance. Okay? So if you cannot have negative distance, you cannot have negative energy. All right? It's always positive and it's usually quadratic in essence. So there is no such thing as a negative energy. Right. Coming back to the example. So we choose, usually for this type of thinking, you choose an energy function. You'll see that even for physical systems, the energy functions, they are not unique, by the way. They are just physical conventions, what we learned. Kinetic energy, potential energy, this and that. These are just physical conventions, but they're not unique. There do exist energy functions which have no physical meaning. They are just some positive functions of the variables of the systems. Okay, we'll see this very interesting fact. So, and what happens? You want to see the growth or the decrease of energy. How do you do that? You take the time derivative of the function, okay? And if this time derivative is negative, if this time derivative of the energy is negative, okay, but this is not negative because this is minus x squared. If it were negative, okay, if it were negative, you would see that the equilibrium point is stable. Well, in this case, it's undecidable taking this energy function. So this is not a good, in quote, good energy function, because you cannot say anything about the equilibrium point, okay? Then we have some other exercises with flows and debits and all sorts of things. You have also this exercise here, okay? So you have multiple equilibrium points here because of the sign, just like the pendulum. Because of the sign, just like the pendulum. So the equilibrium points in this case are of this form, okay? And when you take the graph, you see that they all follow one another. Attractor, repulsor, okay? Attractor, repulsor, attractor, repulsor, and so on and so forth. Then you have this example, x dot is x squared times 1 minus ax squared. Here the equilibrium points are 3, 0 and plus minus 1 over square root a. Okay. All right. Look, you have a saddle point, and here it depends on specific cases. Saddle point for A equal to 0. If A is larger than 0, you have 3 equilibrium points. You have 3 equilibrium points, and you look at this function. You see, a repulsor, a saddle point, an attractor. What I told you earlier. They're always alternating. You can never have the same type twice or consecutively. You see? Unstable, a repulsor, okay? This is a saddle point, and this is a stable point, okay? Then there's also here a circuit with the diode, and a capacitor. It's a simple circuit. You can study this yourself. Here you take Kirchhoff's second law and write the constitutive. You write the conservation law, no, the functioning law of the capacitor. Okay, the law of the capacitor and Kirchhoff's law. It's all enough to construct the solution of this guy. Okay. All right. And you get this dynamical system, and you measure this interesting output. Okay, and you have interesting properties here. It's worth looking at these examples. Okay, it's worth looking at these examples and making the best of them, because you get interesting stuff to look at and to study. By the way, let's go back to. Okay, I'll share this screen once again. Okay. Have you got any questions about the exercises I just showed you? Have you got any questions about them? Mm-hmm. Questions, please. Okay. For some reason, you do not have any questions. Fine, let's go to the shared screen. You can see my maple sheet here. On this part, so earlier I showed you this Riccati equation solution, okay, in this symbolic environment. And now we can build another maple sheet where I can show you different other examples, okay? So look, we had this exercise earlier. Let me just increase the font. Is it better now? Hmm?
It is.
Can you see clearly the equations written in blue?
Yes.
Okay, fine. Like I said, these are all packages you need to, and there's many more. There's thousands of packages Maple has, which you need to load when you need to solve a specific symbolic issue. Now we define here the differential equation which is this one. This is the way to write a differential equation. Okay. We have the initial conditions. I start from 0.5. And this is the command, the line to solve explicitly or numerically a differential equation. Dsolve is the command. Okay, dsolve is the command. Is the tool. And you write in between brackets like this. You write the differential equation that must be solved, and together with the initial conditions where it has to start. If you do not write the initial conditions, I'm showing you, then you get a general version of the solution, okay? For any constant, you see, and you have like this. So depending on the initial condition, you can get either a plus solution or a solution with a minus, depending, like I said, on your initial conditions. Okay, so now I have the initial condition. Okay, what happened now? Oops. I did something wrong. Let me run this, because I can run a piece, only a piece of this maple sheet. I'm running this piece once again. Okay, probably it was a problem with the variables, because sometimes they repeat themselves and he keeps the last version of the variable. So a restart, by the way, is the same like clear all in MATLAB. So this is the solution for this initial condition. You see the explicit solution here. So when t goes to infinity, this solution is going to 1. You see the equilibrium. This solution is going to 1. And so the equilibrium points here, I didn't solve the equilibrium points, but it's easy to see that they're 0 and 1. Well, now I would like to plot the solution. You know, to plot the solution, you need to numerically solve the solution, so you can get data sets. Okay, so here the solution is written in data sets. Hence, you just need to introduce here the type of solution that Maple needs to do. Okay, so you can tell Maple the type of solution you would like him to provide for you, to deliver to you. So here we'd like to solve this numerically, so we can get the data sets in a specific range. You see, this is the time range, and then to plot the solution, you use the specific function ODE plot. The typical function to plot a graph is plot, as you can see here, just like in MATLAB. Whereas when you'd like to plot the solution of a differential equation, you need to use ODE plot. So this is the numeric solution. This is the way Maple is providing, or is delivering the numerical solution of the differential equation. You can see here that it's using the Runge-Kutta. So this is just like ODE 4.5. You see here, Runge-Kutta function of order 4.5. Okay, so this is the numerical integration tool Maple is using to deliver the solution. And this is the plot. As you can see, just like I said earlier, it leaves 0 and it goes to 1. And the solution is in this band between 0 and 1. Let's see what happens if you take a negative initial condition. And it's the same. No, it's not working. Why? Because probably. Sorry about that. What happened here? Oh, look. This is the other type of solution. Is going from 0 to the other equilibrium, -1. You see? If the initial condition is somewhere in between 0 and 1. Is the other band. Okay? You can see now. Now let's see what happens if you take a less than one initial condition. Let's see. I run Well, you see, it's a vertical asymptote. It's a vertical asymptote. You see, just like we had earlier. Here we have the so you see the bands. Yeah, okay, so this is the semi-line. Okay, this is the semi-line. Okay, I'm trying to use the properties of the axis because I would like to have them from -5 to 5. So we can explicitly see, you see the vertical asymptote here. We have the vertical asymptote, okay? So this is just like we saw the things earlier. And when you do this, you probably have something like this. You see, vertical asymptote, okay? It's coming from somewhere, vertical asymptote to the left, okay? It's a bit different than the second order equation we saw in the first example, in the Riccati equation actually. It's different, okay? It's not the Riccati because it's x cubed. You see? The vertical asymptote from the negative side. Right. Let's go back to the good case. Let's go back to the good case here. So we just okay. Okay. Now we just plot f of x versus x. Okay, I used here y because if you use the same x, Maple doesn't know that it's a different x. Okay. Look, the function we saw earlier. So attractor, repulsor, attractor. Okay. So 0 is forever repulsor. Okay. Right. This we have this example now. You see the general solution. You can add here initial conditions. Actually, we can use the same initial conditions as previously. We don't need to redefine. So you can do that and put here initial conditions. What happened? What happened here? It's not working with those initial conditions. What happened? We solve. Let's see. Oh, here you cannot use x. That's the idea. Let's redefine the initial condition. Something is wrong. Probably I shouldn't have used it. I don't know what's actually wrong here. Cannot solve this. So initial conditions, okay. No, there's something wrong.
You need braces.
What?
Inside. Braces.
Where?
Coladele în dissolve.
Where? Oh, in dissolve. Oh, sorry
Yeah.
about. Oh, the brackets. Okay. But it's still not working. Cannot be assigned. What happened here? Let's run this again. Oh, it works now. Okay, so, okay. Yeah, so you see here, it's 1 over t. Okay, you see the vertical asymptote here, once again. Okay, let's see what happens if you take this. I'm running the whole sheet once again. So it's pretty much the same. Yeah, the vertical asymptote, because of this, you see, in t equal minus 10, there is a finite escape time of this system. It's always going to have that. Yeah, look, this is even better to see. You see, with negative initial condition, in t equal 10, there is finite escape time. It's finite escape time and no equilibrium point. No equilibrium point. Okay, as you can see. Yeah, finite escape time. Then we have this. We know already this equation. Yeah. Then we have this interesting equation here, this one with a square root, and this is the interesting solution of this guy. Let's see if I do give it initial conditions. Oh, sorry, again, the brackets, true. Oh, sorry. I cannot use ICS. I need to redefine ICS. Redefine ICS. ICS. Equals 0.5. Hold on a second. Okay. So ICSF. It's not doing anything. Why? Interestingly enough, because of this B guy, it's difficult to solve this. You see? It's difficult to solve this. Anyway, all sorts of examples, okay? We can see here. So we can easily integrate and use Maple to solve our exercises for us and show us the solution and show us the equilibrium points and emphasize all of this. Okay. I don't know what this is. I mean, I know what it is, but I don't know why it showed up here. I just want to show you. Okay, so here on Moodle, we are in this week, okay? Today is the 20th of October, right? So please do try to solve assignment 4. Okay? Assignment 4. Today is what? 20, right? October. So it will be open from 6 o'clock. And I can leave it like this, open until the 6th of November. Okay? Please solve and upload. Okay? You can upload reports, you can upload software, MATLAB, Maple, whatever you like. Okay? Please respond to mFile script and PDF comments suddenly. Okay? So you can solve assignment, or I'm asking you to solve assignment 1. Okay? Please M Maple, MW. That's the extension of Maple. Okay. Okay. You need to solve this assignment. Can you see the assignment?
I saw it today when I
Yes.
entered the Moodle. But if you change the hour to 6 o'clock, maybe now it is not visible.
No, it starts at 6. You want to see it now or what?
Yeah, this is what I meant, that right now it is not visible. But
Okay,
it will
fine.
be. Yeah.
The settings
But it's not a problem.
No, I'll start 5. I'll make it 5. Okay. It's 17, that is. No, check again.
I can see it.
Yeah?
Yeah, I can see it too.
Okay, fine. So you need to solve this and upload report and upload software, okay? Do something, work it out. It's nice, okay? You just need to do numerical integration. You just need to understand. We did today quite a number of examples, okay? So this is pretty much based on chapter 1 and what we did this part of chapter 2, okay? Right? Well, in my perspective, I think this is enough for today. Do you agree?
Yes.
Right.
Yes.
So do your assignment. Have you got any questions about everything we discussed today? If you have questions, comments, please tell me now.
I don't have any questions, but I see that I still enjoy the lecture.
Oh, that's nice.
It's
well, it's going to be harder and harder actually.
yeah.
So if you enjoy it, then that's well. If you do get a grip, if you grasp the meaning of the stuff I'm telling you in this chapter, you can easily decipher or partly decipher what's going on in the chapters. You realize we are going to increase the dimension. You can look through the slides because you have all the slides on Moodle. You can look in advance and you can see what's in store for you, so to speak. Okay. So you'll have another few assignments, and then you need to study the papers, and you need to write a report of those papers, and okay, for your final examination and so on. Okay. So the assignments will give you points for the activity during the lecture, and the papers are for the final exam in January. Okay. Agreed?
Yes, yes, it is clear.
Well, that being said, well, stay safe, and hopefully I'll see you all fine and all right next week. I'll see you in good shape next week. Okay. Right?
Okay.
Okay, fine. Well, cheers, everyone.